Some of the Big Bang Theory's validity. In light of the new data discovered by the James Webb Space Telescope is under scrutiny. We just made an unexpected discovery that is transforming the world of physics. The most recent picture taken by this telescope has produced persuasive arguments that have surprised experts, putting a stop to a lot of speculation. The telescope's most recent discovery is visually stunning and could transform our comprehension of the cosmos. The experts' discussion of this image, which has been resolved, focuses on the perception of the cosmos. The stunning image that was taken by the James Webb Space Telescope challenges our understanding of the universe. One of the main problems in astrophysics, the universe's age and the rate at which it expands, is addressed by this finding. Researchers from various generations have been puzzled by this unsolved phenomenon and have carried out a lot of studies looking for answers. Cosmologists investigate how the universe originated, how it works, how it has changed over time, and how it could end. Over the past century, great advances have been made in this field. The Big Bang Theory, the most widely accepted theory in cosmology, holds that since the beginning of time, the universe has been approximately 13.8 billion years old, starting from an extremely hot and dense state. The Hubble constant, which indicates the speed at which the universe expands, is used to quantify this expansion. However, determining how to measure the Hubble constant is not straightforward, and there are two primary approaches: local measurements and measurements of the early universe in space. Items such as stars and Typea supernovae, which are used as standard candles because of their consistent brightness, allow astronomers to determine their distance and, as a result, compute the Hubble constant. As the universe expands at varying speeds over time, scientists can figure out the Hubble constant accordingly. There are two main approaches. One is the measurement of the initial universe. Scientists employ readings of the cosmic microwave background radiation (CMB) 1960s as the Big Bang's lingering glow. This microwave energy comes from when the universe was only 380,000 years old. Astronomers can determine the age of the universe and its expansion rate by taking note of the minute ripples in temperature and polarization emitted by the CMB. There is, however, a problem. The results from these methods are not the same. Local measurements suggest that the universe is expanding faster than the CMB data suggests. Scientists have been working hard to understand why the results differ. To unravel further enigmas of the universe, research is underway. The distinctions in measurements suggest that we do not yet comprehend all of the warning signs or that there are mistakes in either one or both methods. However, thanks to the James Webb Space Telescope, we can peer farther into the darkness than ever before, revealing elements, planets, and galaxies we never thought possible. Scientists hoped the data would help them calculate the Hubble constant, but the first wave of data has revealed unexpected results that don't line up with existing expectations. Can this information give us new insight into space? We might need to rethink what we understand about the workings of the universe. We might discover particles and forces never seen before, or we may find that the unknown force known as dark energy, accelerating the expansion of the universe, requires reconsideration. With each new discovery, our concept of space changes. Take, for instance, the cosmic microwave background radiation discovered in 1965, which provided solid evidence of the Big Bang Theory. Prior to that, scientists believed the universe would last forever, expanding at a constant rate continuously. However, new evidence showed this was not the case. In the late 1990s, when it was found that the universe was accelerating in its expansion, scientists also learned about dark energy and its impact. Every time we discover something new, we test whether it fits with previous knowledge and develop new ways of understanding the universe. Without this process, the challenges we face in cosmology could not help us gain more knowledge. Although this problem is complex, it is also exciting because it drives us to develop better tools to explore space. Scientists around the world are enthused about these discoveries. this cosmological puzzle, because everyone desires more information about the universe, is compelling. Most importantly, it demonstrates how science is always changing as we gain more knowledge of space. Structure-age tension is another concept that goes hand in hand with Hubble tension and refers to how matter is distributed in space. We use this information to model the structure of the universe and observe how it has changed over time. There are many galaxies in some parts of space, clustered together, while others are relatively empty. Scientists use different methods to determine the magnitude of this dispersion. One possible way to address this is to look at how various material densities, such as galaxy clusters, bends light from faraway galaxies. This phenomenon, known as gravitational lensing, makes it possible to see the effects of dark matter, which, because it does not produce light, is undetectable. Also, scientists look at the cosmic microwave background CMB radiation, the afterglow from the Big Bang. This light has traveled for about 13.8 billion years, carrying information from the early universe. By studying the CMB, scientists can understand how the universe was full of irregularities when it formed. However, this data does not match the large-scale irregularities observed in the current universe. The non-spherical distribution of gravity suggests that matter in the early universe was more uniform than what is observed through gravitational lensing. This implies that something fundamental is missing in our interpretation, bringing us back to the mystery of dark matter and how it operates. According to Rice, he and his team were able to redefine their work thanks to the James Webb Space Telescope and wanted to see if there was a chance error in the Hubble Space Telescope's measurements could be the cause of this discrepancy. However, the JWST showed the same deviations, which is worrying. Somewhere between these two observations, there must be a fundamental flaw in our understanding of the universe, Rice said in an interview with an astronomical magazine in the United States. Using the new space telescope, we can now see further into the universe through its sharp infrared view and study cosmic distances with ever more precision. Both dark matter and dark energy are enigmatic components that make up a significant part of the universe, but their nature remains elusive. While black holes have been the most prevalent explanation for gravitational effects, there is growing interest in exploring how dark matter and dark energy may have an impact on these cosmic phenomena. Please inform me of your opinion in the comments box. If you want the video, don't forget to like and subscribe. Thank you so much for watching, and I'll see you in the next one. Thank you. As scientists continue to analyze data from the James Webb Space Telescope, which laid the groundwork for cosmology, they are facing unprecedented scrutiny. The telescope's ability to observe far-off galaxies from a few hundred million years after the Big Bang has posed a challenge to existing galaxy formation models. Contrary to prior presumptions, the initial universe appears to have hosted more massive galaxies than anticipated. These findings suggest that either galaxy formation occurred much faster than previously believed, or what we knew about the physics governing the early universe needs to be completely revised. One emerging theory to explain these discrepancies involves modifications to the current lambda CDM model, the standard model of cosmology, which includes cold dark matter CDM and a cosmological constant lambda representing dark energy. Some physicists propose that dark energy may not be constant at all, but instead may change over time or interact with dark matter in unknown ways. This dynamic form of dark energy, sometimes referred to as quintessence, could potentially account for variations in cosmic expansion rates observed at different epochs. Other researchers are exploring alternative models of gravity, such as modified Newtonian dynamics MONT or scalar tensor theories, which propose modifications to the general theory of relativity at cosmological scales. These theories attempt to explain phenomena like gravitational lensing and the absence of cosmic structure without invoking unknown entities like dark energy or dark matter. While controversial and not yet widely accepted, these ideas highlight the increasing readiness of scientists to question long-held assumptions in light of brand new observations. The JWST has also opened up opportunities to examine the atmospheres and chemical makeup of exoplanets, some of which orbit in the habitable zones of their stars. These studies may not directly impact our understanding of cosmological expansion, but they provide important context about how matter and stars change systems and the potential for life in the universe. The chemical fingerprints JWST detects in these atmospheres can also provide information about the larger distribution of elements in the universe, another important piece of the astronomical conundrum.